Hello guys, in this lecture I'm going to go over the DH transformations in detail. And so the DH transformation is essentially another type of it is a form of a homogeneous transformation, which we said last time. If I have a homogeneous transformation, let's say I'm calling that H01, it entails having a rotational transformations as a 3 by 3 matrix, and we have 0, 0, 0 below that, and then we said we have a 1, 0 where this guy is 1, right? And by now, all of you should be able to build a homogeneous transformation between any two transformations. So if I gave you base frame x0, y0, z0, and I gave you another one like that, x1, y1, and then z1, right? And then this is 0.01. You should be able to build that matrix, right? And then I will very briefly do that because this is very important. So what is the first column of the R01? It is what? It is x1 in frame 0. So all I have to do is express that vector x1 in that frame. So essentially, I would look at the x component of the vector x1, I would look at the y component of this vector, and then z component, and then I would put that here. That would be a 3 by 1, and I want to have that 0. And the reason why we have the zeros and the 1, excuse me, is in order for us to be able to multiply these homogeneous transformations, right? And the second vector here is going to be, that should be y1, 0, and then z1, 0, and then the last one is o1, 0, and then 0, 0, and then 1. So if I have any vector in the first frame, in frame 1, I can literally multiply it by that, and then I can get the coordinate of this point. Let's say this is, vector p. If I ask you for p1, right, what is p1? P1, basically, you would look at, whatever, you have your x1, y1, p1 for this vector p, right? And obviously we said this will always have, so let's say this guy have x1, y1, z1, right? If I multiply this guy by here, I would be getting the coordinate of this tip in the base frame, right? But then if I ask you to only perform rotation on this vector, basically you will put here 0 instead of the 1. And by doing so, you will be getting the projection of this vector, literally like this, the projection of this vector into that frame. You will be getting the x0 component of this vector, the y0 component, and then the z0. You can also think of this as you're taking that vector and then you're putting that here, and you are finding the projection of this vector into that base frame. Okay, so this is a homogeneous transformation. Now, what is a DH transformation? A DH transformation is also a homogeneous transformation, but sometimes it's actually difficult to, if you have an industrial robot, it's very difficult for you to sit down and then find what is x10, y10, z10, and o10. There is a lot of variables, so each one basically will have here 3 values, 3 values, 3 values, and 3 values. So in total, how many values you have? 3 times 4, almost you have 12 values to define that homogeneous transformation between those two. So people have come up with another way of doing that, which is a DH transformation. And it turned out that all we essentially need is we need basically 4 values to be able to create that. And however, we need 4 values if we build the transformations in a way where, let's say I have a base frame. Okay, let's say I have an x0, y0, z0. I would have to build a second frame so that my x1, right, is perpendicular to both z1, right? So let's say this is my z1, right? So this z1 is going to be a free vector, okay? But I'm always going to be able to put a vector x1 that is perpendicular to both, right? Z0 and Z1. So this is going to be my x1. Okay. So if I do that, all right, this is now a DH transformation or the DH frame basically. So this is a valid DH frame. And the reason why it is valid is because my x1 is perpendicular to both Z1 and also Z0. So remember, guys, this is very important. All right. And then I want to be able to define, okay, theta 1 is essentially the angle. This is my theta 1. And Z1, by the way, doesn't actually have to be parallel to Z0. It could be in any direction, and then I would still be able to write that as a perpendicular. And we're gonna say D1 is gonna be this distance from here to here, from x0 to x1 along Z1. Okay, and then we have alpha. Alpha is the angle between Z0 and Z1 about x0. So by how much you are rotating Z0 to come to Z1. All right, and finally alpha. Yeah, that is alpha, and then basically we have A1. What is A1? A1 is going to be that distance, right? Distance between the Z0 and then the Z1 axis. Okay, this is the A. So my DH transformation is, I can, now I want to actually look into here, into my presentation that I have, and you will see that my DH transform, okay, what is the mouse? All right, so my DH transformation for N2 frames basically, which are already DH frames, meaning x1 is perpendicular to Z1 and also perpendicular to Z0. I can write that DH transformation is that, you know, first you rotate about Z, right? So remember how we can do the sequence, right? So from left to right, I'm going to try to move the first frame and then I'm going to put it into the second frame, right? So initially you rotate about Z by theta, right? So I'm going to rotate by Z by theta. So now my x0 is pointing along x1. Again, on this figure, the same thing, right? So this is my Z0, this is my Z1. I'm going to rotate about Z. So now my x0 is going to be pointing toward x1. Then I'm going to translate along Z, right? By a distance of D1, right? So I'm gonna translate along Z by a distance of D1. Now, basically, these are collocated kind of, right? Now my x0 is here and it's pointing toward that. Then I can translate about x, because x0 is in the same direction as x1 right now. I can translate along x, right? So now my x0 is here. I can translate along x by a distance of D, right? So now I'm here. And this figure, basically, alpha would be 0 because here I kind of drew Z0 and Z1 to be parallel, right? So the last thing is you want to rotate about X, because sometimes your Z1 could be like that, right? It doesn't have to be, in this case, like both of those are like kind of vertical. You would still have to rotate about X by the angle alpha. So you could bring Z0 into Z1. Okay, so rotation about X basically is you're going to rotate Z0 about X1 in order for you to bring Z0 to Z1. Here, alpha is kind of a little bit weird, but I think here alpha, it should be in the opposite direction, not in that direction, right? Because you are rotating about X1, so by how much you want to rotate Z0 in order to bring it to Z1. And then this is the angle that is parallel to Z1. So here it should be this angle. Let me actually draw it for you guys. Okay, so this should be basically my phone. Okay, I don't like this, so let me. Okay, so this is my alpha. Okay, this is wrong here, okay? But you got the idea, right? So alpha is that rotation, that final rotation between Z0 and to bring Z0 into Z1 about what? About the initial vector, right? Because we're moving from the first frame to the second frame, all right? So now the DH transformation is only applicable only and only if you drew x1 to be perpendicular to both z1 and z0, and you have the rest of these values. Okay, so it is a function of 4 variables. And when you buy an industrial robot, right, like a KUKA robot or all these, you know, brands, they will actually give you a table, right? So each link, right, each link will have that transformation, right? So you will be able to use that. So trans times rotation about x by alpha 1. So each link, I'm gonna call it link I, right? You're gonna have theta d a and then alpha. Okay, so each link basically will have its own row, And sometimes this is a variable, right? So this is a variable, and then here, you would have the values like, 0.5 meters, A would be, 0.01 meter, this would be like, usually 90 degree, usually alpha is either 90 degree or, or 0 or minus 90 degree, right? You don't, and the reason why is that is because, sometimes, remember what the z-axis is, right? Maybe I forgot to mention that earlier, that I did mention it in the previous lecture, that the z is the axis of actuation, right? So if I have the first motor is like that, so this is your axis of actuation, right? If my second motor is like that, basically, then this is my z1, right? So here alpha, remember alpha is always the angle between the axis of actuation. So if this is like that, and then this is like that, basically this robot is trying to, rotate like that, and then it's, spinning this guy like this, right? So here, this guy is doing that. Okay, we're gonna do a few examples on that, and I think you guys will be able to get the hang of it very quickly. All right, but remember, right? So we have two ways of doing transformations. You could make your own robot, right? And I'm sure many of you can do that, basically. And to do this, you will have to write, these vectors and then get the values of what x10, y10, z10. Well, here in reality, you don't really need 12 values, right? Once you know x10 and then y10, z10 is theoretically the cross product, right, of x1 times y1. So you don't actually need that. So in reality, you need 9 values. Either any 2 vectors here, and then the third one would be the cross product, right? And then finally O1. And regarding the cross product, how do you do that, right? You have x, y, z, x, y, z, right? So x cross y will give you z. So this is the easiest way for you to look into that. So x cross y will give you z. Y cross z will give you x. So if you are going from left to right, you are going to get a positive value, right? But y cross x will give you minus z, okay? And then x cross y, right? So, x cross y will give you what? Will give you z, right? But then x cross z will give you -1. So you guys want to be familiar with that process and then how you actually do that, okay? So the alternative way is the DH transformation, and the DH transformation is when you have a robot, initially you're gonna put your axis of actuation, right? And this is, the Z is always along the axis of actuation of the motor. So this is, if this is, this is a, okay, let me just do that really quickly here. Okay. If this is a motor, this is a gearbox, then this axis is really along the axis of actuation, right? And then this is a second motor, your Z1 is along the axis of actuation. For a rotational joint, for a prismatic joint, like a, like a piston, right? If you have a piston type joint, right? Then your Z is actually also along the axis of actuation, right? Linear, I'm gonna call it linear. So this is your Z linear, right? So this is like a piston that is trying to move. Let me even do that even more clearly here. Okay, so this is a piston. So if you have a piston type actuator, or we also call it a prismatic. So this is a prismatic joint. And virtually these are the only 2 types of joints that you are going to see: prismatic joints or rotational joints. Okay, let's go back to my lecture notes. Delete that and this. Okay. So again, this is what I have here. So each link basically will have the DH transformation, and for link 1, you are obtaining the DH between 0 and 1, right? So if you know A1, alpha 1, D1, theta 1, and the axis of actuation usually is either theta 1 if it was prismatic, right? The variable basically in that DH transformation is either theta 1 if it was rotational. So you are rotating the first link, right? You are rotating the first link about, I'm sorry, you are the second link, right? You are rotating this about the first link. The first link is gonna be basically the ground. Okay, let me rephrase that. When you are rotating theta 1, so your x0, y0, z0 is always along the base frame, right? So let's say your robot start here, okay? So this guy is fixed. So this is my first motor, right? And basically I'm gonna do my Z0, right? The first motor is connected to ground, right? So this is my, so I'm actually free to select where X0 is, but obviously this has to be an orthogonal frame, right? Now let's say this guy is driving another link like that, right? So this guy is the ground, right? This guy is the first link, and this is a motor on the second link, right? So this is this part of the motor is connected to ground, right? This guy is your first link. Does it make sense? So this is our first link right here. Okay. This is connected to ground, so it's part of the ground. So Z0 always have to be on this guy, right? On a ground component, whatever that is fixed to ground. Z1 have to be connected to link 1, right? And then this is the motor, this is the axis of actuation, then this is my Z1. And then that Z1 is a free vector, basically. Anywhere that you put it, it doesn't really matter, right? But now when I want to put X1, X1 have to be perpendicular to both Z1 and Z0, right? So this guy is going to be my X1, okay? So whenever that I'm doing my DH transformation, right, the DH01 will give me the DH transformation between the base frame, this guy, and that frame. So if I have a vector expressed in that frame, I'm going to be able to actually express it here. All right, so this would be my DH01. I'm going to have, A1, alpha 1, D1, and then theta 1 for this guy. If I look to this guy from a top view, what am I going to see? Just so you guys can see that. So I want to see this guy. I want to see X0 like that. I want to see Y0 like this. And this is my first link. And then I'm going to draw it to be a little bit kind of offset. So this is my second link, right? So X1 has to be what? Perpendicular to, so this is my Z1, right? And then my Z0 is also pointing up, right? So this is my Z1, this is my 0. Now X1 has to be perpendicular to this guy and that guy, right? Okay, I'm not going to draw Y1 because I already know Y1 is going to be the cross product of X cross Z, right? So how would that look like? So theoretically, it's going to look toward that direction, but you never need to draw Y1 on the DH frame. Okay, so if I want to actually build that DH frame for these two vectors, so DH01, right? What is that going to be? It's going to be a function of, I need to know A, alpha, D, and then theta, right? What is A on that figure? We said A is going to be equal to what? We said A is going to be the distance between the z-axis, right? So what is the distance between the z-axis? It's going to be that distance right there, right? And that is a fixed distance, okay? So A is going to be equal to L. We said alpha is going to be back to here, right? So alpha is going to be, you are rotating z0 about x to give you z1, right? So here, by how much are we rotating this vector, right, in order to come here? By 0, right? Why? Because z1 is actually parallel to z0. So alpha is 0. And then we said d is the actual offset, right? So is the offset of x0 to x1. So that is the distance d, right? So you want to continue this guy like that, and then that is going to be your distance d. Okay. Let's call that d0 just so we can have some value. And then what is the angle theta? Okay. Theta is what? Theta is the rotation about z0, right? About z0 in order for you to bring x0 into x1, right? So you want to bring x0 into x1, right? This is angle theta. Okay, in a very layman term. So theta is your actual variable. All right, so when I actually plug that into my DH transformation, I'm going to essentially get H01, right? So H01 is gonna be my DH01, but now basically I've literally built that homogeneous transformation using only these 4 variables. Let's actually look into what are the actual, how would the actual, the inside of the DH transformation look like. Okay, just very quickly. Okay, so this is the DH transformation, right? This is rotation about z by theta, translation about z by d. This is what it is, right? Translation about x by a, right? And then you take about x by alpha. Literally, I'm building this from the elementary rotations and rotation and translations we've already developed in our course. You end up with actually this guy. So this is your DH transformation. And now you can actually create that as a function in MATLAB, and then the argument for that function are going to be what? So it's you will give it basically D, A, alpha, and then theta all as symbolic variable or whatever values that you could have for D, A, or alpha, and then it will be basically a function of theta. Okay, so this is the DH transformation. Now I'm going to kind of get into more detail into the stuff that I just explained in a more, as a kind of procedure for doing that. So placing the frames on the manipulator, right? Like I said, the first step you have to do is you have to draw the z-axis, right? Or the actuation axis, such that they are in the direction of actuation. If it was a rotational joint, right? This is a motor, right? So this is a shaft of the motor. Your z has to be along the shaft of the motor, all right? If it was a prismatic joint, your z vector has to be along the linear piston, right? Linear piston axis, also the axis of the piston, or the shaft of the piston, basically. Okay, this is the first step that you have to do. You want to put your z axis. Okay, the second thing, and then this is where most people, make mistakes, and you have to draw your x1. You've already established your base frame, right? Your home frame, or your world frame, basically, which is x0, y0, z0, and then also z0 has to be along the first axis of actuation. Now, your second step is to build x1. x1 has to be perpendicular to both vector z1 and z0. So this is very important, and some people tell me you will always be able to do that from a geometric perspective. Okay. For any two vectors in space, you are always able to draw a vector perpendicular to this guy and also perpendicular to this guy. Even if they are parallel or not parallel, different planes, whatever, you will always be able to actually draw that. This is the essence of the DH transformation. And once you have the Z, basically, that's it, you can get the Y. Okay, now in order for you to actually find alpha, we said alpha is you are rotating Z0 about the previous X in order to get to Z1. Remember, we're actually starting from the base frame, and we're doing that sequence of rotations in order to bring the base, right, or the frame 0 into frame 1, right? So you're gonna apply that sequence from left to right. So alpha is gonna be a rotation about X, right, of Z0 to bring it into Z1, okay? There's one thing here you wanna make sure is, basically, yeah, so alpha is by how much you wanna rotate Z0 about, essentially here it's just the new x-axis, right? Not the old x-axis. This is the only difference that we are going to do here, right? So you rotate about xi, not xi minus 1. So you want to see the new xi vector, right? So you've already drew the new x vector, right? You want to see by how much you want to rotate the older z-axis to bring it into the current z-axis. Second step is easy step. What is theta? Theta is by how much you are rotating x0 about z0 to bring it into x1. Right? Okay, so Z0, let's say this is your Z0, this is your X0, right? I know X1 is perpendicular to Z1 and Z0, so it's already perpendicular to Z0, so I can do that. So by how much I'm gonna rotate that to actually bring it into X1? Very easy, right? Step 5, label origins of the frame. Obviously, this is very important. Not you are free to choose any convenient frame for the end effector, however. Okay, so toward the end effector, obviously, when you are at the end of the robot, basically, you will be able to choose whatever frame because you no longer have any axis of actuations. Only at the end effector, and I'll let you guys also kind of think about that so you can kind of challenge yourself a little bit. And the last step is to basically find the D's, right? The D's is the distance between the X's, right, along the Z's, right? We've already explained that, right? So the D in this figure, right? The D is the distance between X0 and X1, X0 and X1 about Z0. Okay, so this is your D. Okay, deal? So that's it. Okay, this is my DH transformation. Again, to be able, okay, so very important, guys, X have to be always perpendicular to Z1 and then Z0. Once you do that, basically, you have a valid DH frame. And what I've done here in MATLAB is I programmed this function that I just showed you, right? The sequence of, you know, A, alpha, D, and then theta, and now I actually have that here. So the arguments here are you have to pass basically A, alpha, D, and then theta. If it was rotational joint, your variable would be theta. Your symbolic variable is going to be theta. If it was a prismatic joint, your symbolic variable is going to be D. So guys, you can now use these building blocks to build really modern robotic systems, and you can really kind of begin to comprehend and understand really how, you know, robotic manipulation essentially works. Literally, like the basis of that is to really understand, you know, frames and how I can basically go from one, you know, one frame into another. Later, we're going to use these to be able to do kind of the inverse kinematics of these. Essentially, we're going to be able to find, you know, what theta should be in order for this guy to be the desired position. Okay, so this is my DH here, and let us actually do a brief example, right? Let's say we have this robot, right? And this is the robot in example one. Actually, how does it look, right? So let me, this is like a serial robot, right? Serial, you know, rotation. You know, sometimes they actually label robots as R, right? It kind of, you know, calls the kinematic configuration of the robot, like R for a rotational joint, R. This guy could be prismatic, so it would be like RRP or whatever, right? Most of the robots that we deal with nowadays are rotational, but obviously there are still a lot of robots that actually have prismatic joints, and usually they are used in different types of, you know, pick and place applications, etc. So how would this guy look like if I were to actually draw it, right? So I'm gonna have the first joint, right? And usually I like to draw the joint as like that, right? So this is your what? This is the motor, and that is what? The gearbox, right? Later on, we're gonna get into, you know, the gearbox and the dynamics of this joint and then how it actually works. So this is your robot, basically. You fix your motor, right? The motor will have like, you know, 4 holes at the back. You wanna fix that into like, you know, some kind of a plate here, right? Okay, so this is your motor. This is the first, so this is the shaft of the gearbox. And then here, basically, we have like a link, right? Okay, so this is your motor. This is a gearbox or the gear reducer. Now I'm gonna actually put my second thing. And let's say now that I am basically putting my, let's say now basically I'm putting actually my another motor and another gearbox here. So let's say we basically kind of made like, you know, like a bracket on this link basically, right? And then that bracket kind of looks like that. Okay, in a very layman term, basically, it looks like that. And I came in and I attached another motor here on this bracket, right? So that motor is going to look like this. Okay, so this is my second motor. And then this is my gearbox connected to it like that, right? So this is motor 2. And this is second gearbox, okay? So this is all basically one part, right? So the motor is actually part of that link. So now we have, this is a second shaft, and now basically I have another link. And that link is going up like that. Okay? So this is link 1. And then this is link 2. Okay, and that's it. Basically here I have like an arm, right? This is my end effector. Okay? Now I want to establish the DH frames. We said the first step is you want to do what? You want to put your Z axis, right? So this guy is going to be my Z0. Okay, Z0 is the axis of actuation, right, of the first actuator, right? And Z0, guys, is part of the ground, okay? It's on the motor, which is connected to ground. So Z0 is the shaft of the motor, right? Then I have Z1 is gonna be this guy. In this case, they are what? They are parallel, but they don't have to be, but you know, this kinematic configuration, they would be parallel. Now I'm gonna put my X0. I can put X0 like that. I can put it like this. It doesn't really matter. I can put it in anywhere that I want. I like to put it horizontal. Okay, do I need to draw Y0? No, not necessarily, because I know Y0 will always be equal to what? X0 cross Z0, right? So I can do this by my hand. right? And now if I want to put x1, we said x1 has to be how? What is x1 like? x1 has to be perpendicular to z1. So x1, will x1 be along this length or no? No, it will not be along this length, right? x1 has to be perpendicular to z0. It's actually along this length right there, right? So this is my x1, okay? And x1, guys, is along that length right there, okay? This vector is along this length here, right? And then this is my x0. So basically now you guys know that this is your θ1, right? θ1 is the angle between x0 and then x1. So θ1 basically define this, the angle between x1 and x0 and x1. Now how about θ2 basically? What is θ2? Okay, so now basically I'm gonna have to draw another frame on that length. So here I don't have an actuator anymore here, right? So this is my end effector, and now this link here, right? So this frame here is on link 1. This is link 1. Okay, that frame is rotating with link 1. So no matter how link 1 rotate, x1 will always be collinear with link 1. But that link 2 right now, it doesn't have a frame, and we need to have a frame in order for us to be able to express where that vector is, where this link is. So here we are free to choose, and usually what I like to do is I'm gonna actually put x2 like that. So basically I can just mirror that, and then I can actually make z2 parallel to z1, just keep it consistent, and then I'm gonna make x2 is along that link. So I'm free to choose where that guy is. And the reason why I'm doing that is because I know θ will be the angle between x1 and x2, so I'm gonna actually put θ2 like that. Okay, so if I were to look into the DH transformation, right, I'm gonna have A, alpha, D, and then θ. Let's call it I, and then we have link 1 and then link 2. Okay, link 1 will give you the homogeneous transformation between the base frame and then link 1, and DH2 will give me the transformation between link 1 and then link 2, right? Ultimately you will have H02. So if I have a vector in that frame here, I'm going to be able to see that vector into the base frame, right? So sometimes you can actually have a camera, whatever you want to have, and whatever coordinates the camera see, you'll be able to actually have a mapping between here and then here. So I could have an external camera here that is looking at this, and then this camera could be telling where this robot to go, right? So I can express this point in the camera frame, and then I can know the transformation between the camera and the base, and then the base and this. So I can basically, you know, whatever the camera see this object, I can tell this guy, okay, move along x2, come back along z2, whatever. Okay, what is A in this case? Okay, and you know, on the exam, guys, you want to make sure that you have these guys, right? You have this sequence here, okay? So you can apply that. So A is the distance between z0 and z1. It's actually that length right there, right? So essentially it is, if you're looking at your CAD model, it's going to be that length, right? L1, all right? A is L1. What is alpha? Alpha is the angle between the z vectors, which is 0 in that case. How about D? D is the offset, right? So D is the distance between the x-axis. So I'm going to look at the offset, right, between x1 and x0, right? So it is that distance. It's essentially this guy, right? The way we have it here, basically, I don't actually have the geometry, but I want to show you guys the geometry to be able to have a more understanding of these values, right? So D is the offset, right? When I'm putting this vector, I would simply need to actually capture this value from x0 into x1. So essentially, it's going to be the length of the motor and the gearbox in this case. And let's actually call this guy D1 just to stay consistent with 0. And then θ is going to be θ1. Okay, the second is what? Distance between the z axis, right? So it's L2, it's this guy right there. So L2, what is alpha in this case? 0, because I made it that way. How about the distance D here? Distance D is 0, why? Because X2 is in basically the node here, and then the center of this frame are along the same line, basically, right? I'm not doing any offsets here, but I could do that. I could incorporate an offset here. So 0, and then this guy is going to be 32. Okay, guys, so this is what I wanted to cover on this lecture. I want you guys to really recapture these and then try to really understand what we just described. Really, if you have to watch the lecture another time, watch it. But these are so important in our course, and then this is a big milestone in our course. I just want to kind of continue this here so we can just get done with the example. So after you do this, what do? You basically will do the DH, right? So I have L. So here I need to have D, but if I have D, basically I'm going to plug it into my DH function, right? So I have theta, right? And then here, assuming the length is 1, we put, I'm sorry, no, not the length is 1. This is basically DH01, right? So the length is L1. So L1 will actually come in here, right? So basically you're looking here, right? A, right? So L1 cosine theta 1, L1 sin theta 1, right? This is your DH01, and then DH12 is this guy. Multiplying those two will give you the whole homogeneous transformation. So after you do this, basically you can get the rotation between R01, you can get the coordinate of this point in here, basically simply by doing these DH transformations. And you can look at the X component, right, of your T02. You can look at the Y components of the end effector, basically. You'll be able to capture all of these. Okay, guys, so I'm gonna let you guys work on this example on your own. Try to work on this example on your own without looking at this, all right? So do this problem on your own and try to really understand it exactly on your own. And I'm gonna solve that in the next lecture, and then we can jump into other topics like more robotic articulations, robotic wrists, etc. Okay, guys, that is it for our lecture today.